what I'm asking you to do in activity number 5 is to take these 3 braids, U, V, and W, and each one of them is spelled out here with braid language. U and V are positive braids, but W is not because it has negative crossings in it. So I'll have you generate a diagram of the braid VW using this Sage cell down here. Ask Sage whether or not VW is actually equal to a trivial braid, and then try and reconcile your answers to parts A and B. So this just gives you a feel for what braids look like and what their algebra looks like. And if you can, tie this back to the braid relations, 2-1-1 and 2-1-2, that's great. Otherwise, we're going to continue talking about that as we move forward into the further activities for today. So activity number 5 is where I'd like you and your team to spend about 15 minutes or so as we move forward. The piece of this activity that I want to dwell on a little bit is the question about how to come up with the inverse for a braid. So in this example, you had this braid S2, S1, S3, S2. So its visualization was this right here. So the first crossing that happens is a positive crossing of the second strand with the third, followed by a positive crossing of the first with the second. And the next one is a positive crossing of the third and fourth. And then the last one that happens is a positive crossing of the second and third. So here's our braid that we call U. And the question that's posed here is, what would an inverse to this braid be? How could we find an inverse for this braid? And the reason that I want to talk about it is that both of your groups came up with slightly different answers. And anytime that happens, you know that that's a good time for discussion in the classroom. So let's take a quick look at the 2 answers that your groups came up with. So this is team 2. Your inverse is S2 inverse, S1 inverse, S3 inverse, S2 inverse. So again, compare that with the original braid itself, which is S2, S1, S3, S2. And group 1 inverse that you came up with was S2 inverse, S3 inverse, S1 inverse, S2 inverse. So the difference between your 2 answers, if you look at them kind of in succession here, is the S1 inverse and the S3 inverse are in opposite positions. So here's team 2's response, and here's team 1's response. So let's try to negotiate out these differences. Your strategy was to sort of work everything backwards. So you start at the bottom of this braid and ask, what twists do I need to add on the bottom of this so that I end up with a braid that ultimately is trivial, one that if I grabbed both ends and I just yanked on the strings, that they would all be untangled, right? And we would just get no crossings all the way from top to bottom. And so what was the first crossing that you put in your inverse?
S2 inverse.
S2 inverse.
So ideally that puts purple underneath red.
Yeah, it puts purple, as you say, it puts purple back underneath what used to be the red. So it's because it's an inverse, that means it ends up being a negative crossing, which means that if I sort of sketch this in here, it means that the northeast to southwest is going to pass as the overstrand. So that's what we would get there as S2 inverse. And if I just pause there for a second, I'm interested in how we would simplify this expression that's over here. S2, S1, S3, S2, S2 inverse. What can I do to simplify that expression?
Can't you just drop off the last 2 transitions?
Yes. S2 times S2 inverse. Well, the invertibility property says any element times its inverse is equal to the identity, right? And so we could rewrite this as S2, S1, S3 identity, right? And since the identity has the identity property, if we write it or if we don't write it, we get the same answer. Right? So basically, we are using that S2 inverse here at the end to cancel out the S2 that it's sitting next to. And indeed, if we were to take this braid right now and just kind of pull on the ends, this red strand and this purple strand would just untangle one another. The purple one would slide out from underneath the red one. We would eliminate both of these crossings, this positive and immediate negative crossing. Those two would kill each other, and we would just end up with no crossing there in the middle. So following that strategy, what is my next step?
S3 inverse.
Yeah. So now I need something that can cancel out this S3. Working backwards, upwards in my braid, I need to cancel this crossing that's over here next. And so an S3 inverse would accomplish that. So S2 inverse, S3 inverse. And so S3 inverse brings the purple strand back over underneath the green. Ugh, I'll get this. You can see now I use Sage to draw my braids. It is a lot easier than drawing them by hand. So there we undo the crossing that's directly above it. So if we pull down those, the purple strand and the green strand would now completely slide out from one another. The green strand would slide over the whole purple strand and be untangled with it. The purple strand would slide all the way out from under the green strand and not be tangled with it anymore either. And so what we're doing is, once again, on this equation here, we're just sort of sticking an S3 inverse in there as the next one of my generators. So S3, S3 inverse, that's going to be identity also. And then we continue just by working our way back up. So S1, we would tack on an S1 inverse, undo that crossing. So that would mean bringing this one underneath there, like that. S1 inverse. And then the last cancellation we would need is an S2 inverse. And now we've got it. So what's the general principle here? If you were to describe to somebody, how do you find the inverse of a braid? What exactly have we done here? So for which one of these three equations that we might see in a high school algebra classroom do we really need to worry about the order in which we choose to do the operations that are going to get that x by itself and solve our equation, right? The order in which we need to be careful which one we invert first and which one we invert second. Why is the second equation the only one in which it matters which choice that I make first? Because up here, I could choose to divide by 5 first, or I could choose to divide by 3 first, and it completely would not matter, right? I would end up getting to the same answer either way. Same thing down here. I could subtract 6 first, or I could subtract 10 first, or, you know, however I want to do that. I could do those additions and subtractions in whatever order I wanted. So why is this one different?
So the two different operations involved. You have multiplication 2 times the x and the subtraction -7. So if you're trying to work backwards, you have to do the opposite of what you would PEMDAS. So you have to get rid of the subtraction first, then have to get rid of the multiplication.
That's right. So PEMDAS would tell me that in the expression 2x minus 7, if I'm x, the first thing that's happening to me, according to PEMDAS, is I'm getting multiplied by 2 when this expression is getting built. And then the next thing that's happening to me is I'm adding 7. So that's how I get that expression on the left-hand side. And that's important. The order in which that happens is important, because if we reversed the order, if I did plus 7 and then I did times 2 instead, what would I get? If I add 7 first and I multiply by 2 afterwards, what I get is not 2x plus 7, but twice the quantity, x plus 7, which is 2x plus 14. And so what we're observing here is that the times 2 operation and the plus 7 operation, it matters which order they're done in. Those two operations do not commute as elements of the group of algebraic functions acting on one another by composition, right? The function add 7 and the function multiply by 2 are not commutative one with another. And neither are the elements in the Braid language, right? And so anytime we're working with non-commutative algebraic gadgets, right, we always need to be mindful of that, because if we get the order backwards, we're not going to get what we needed to get out of this. And so the last operation that we do to build this expression, I suppose this should be plus -7, sorry. The last operation that we use to build this expression should be the first operation that we use to unbuild it, right? Add 7 to both sides first, because now we're trying to get that x by itself. We're reversing the order of operations. We're using SADMEP instead of PEMDAS, right? So add 7 to both sides. 2x equals 26. And then divide by 2. So what we're seeing here is an example of an algebraic property that holds in any group, regardless of whether it's an abelian group where everything is commutative, or if it's a group where maybe nothing is commutative. It doesn't make a difference. That what we're seeing is something called the shoes and socks principle, the shoes and socks theorem. And it's called the shoes and socks theorem because it's, the analogy that's usually used is when you put your shoes and socks on, you put the socks on first and you put your shoes on second. When you take them off, you take off the shoes first, and then you take the socks off second, right? You have to take them off in the opposite order in which you put them on. And the way that it looks as a theorem in mathematics is that if I have a group G with an operation, right, and I have any two elements of my group, that the inverse of their product, so the inverse of G times H, is the product of the inverses H inverse and G inverse in the opposite order in which they appeared originally, right? And it's just, again, it's the manifestation of this same idea, right? That the last thing that was done had better be the first thing that's undone. Otherwise, we can't guarantee that it's all going to get undone the way that it needs to. So that's how we can use the shoes and socks principle to discover the inverse for an element of a group that's built out of a language of generators.